Okay, so we were doing differential equations last time, remember? We're doing differential equations. We started off with a very simple differential equation. If you have something that's something like the rate of change is equal to some constant times the function, right? Then it turned out that y had to be a particular kind of function, right? What did it turn out to be? The exponential function, right? It turned out to be, it turned out to be something like this, right? Okay. So this sort of thing resulted in so-called exponential growth or decay, depending on whether or not the constant, if k was positive, then you get what's called exponential growth. If k was negative, then you get something called exponential decay. Okay, and probably, I kind of expect that you've seen this before in your pre-calculus classes, right? No? Okay, so some people are shaking their heads no. That's okay. That's good. Good. Then thank you for letting me know that. In that case, I will talk a little bit more about this. Okay. So the kind of standard examples of exponential decay, exponential growth or decay are, well, for growth, one usually uses money in a bank, and for decay, one usually radioactive material. One usually talks about how radioactive material. So these are examples of things that undergo that undergo exponential growth and decay in the real world. Okay, so okay, I don't want to talk too much about it, but let me just say that in the case of money in a bank, when you put money in a bank, then your money. So if they say that you have a like an interest rate R, okay. Like suppose this R is 5%. That'd be crazy. Nowadays, there are no banks that will give you 5%. But a long time ago, there used to be banks that give you 5%. Nowadays, I think the interest rate, if you put money in a bank, it typically grows at like 1%, at a 1% rate. Well, what does that mean? What does that mean that it grows at a 1% rate? It actually means that that your money is going to be grow like e to the RT. Okay, your money is going to grow like e to the RT times your initial amount. Okay, so this P0 is your initial amount, like how much you put in at time 0. So you see that when you put in 0 for t, then you're going to get P naught e to the 0. Well, e to the 0 is 1, right? So you can see that this P0 denotes your initial amount. So suppose you have $1,000, okay? You have $1,000 and you put it in a bank, and the bank says, so suppose you have $1,000, okay? And there's this bank, and the bank says that no, you don't put it in the bank because the bank is only going to give you 1% interest. You decide to put your money in the stock market. Okay, stock market for a period of time, for a long period of time, used to average about 10% growth every year. Nowadays, it's like 6 or 7%. So let's say that the rate is 0.07 now. Okay, so you decide to put your money in the stock market. You say, okay, well, what's going to happen? What's going to happen to this money over time, on average? Well, now let's use the bank. Sorry, we're going to use the bank. Okay, because the bank actually is guaranteed to do this. The stock market, who knows what will happen? Who knows what will happen? Okay. So you put your money in the bank. It gives you your 1% interest. You're wondering what's going to happen to this. What's going to happen to this money? So P of T is your $1,000 times e to the 0.01 t. Okay. Okay. So you think I'd like to know when this $1,000. Every year the money is going to grow a little bit, right? You're wondering. I'd like to know when my money is going to double. Okay. You'd like to calculate the doubling time. Let's calculate the so-called doubling time. Doubling time. How long it takes for your money to double? Okay. So you'd say, okay, well, I'm wondering when my P of T, you want to know when P of T is going to be 2,000, right? When P of T is going to be 2,000. Okay? You say, okay, well, that's easy enough to calculate. Say, okay, well, 2,000 is going to be 1,000 e to the 0.01 t, right? And so you say, okay, I solve for t, and you get 2 is equal to e to the 0.01 t, right? In other words, the natural log of 2 is 0.01 t, right? In other words, t is natural log of 2 divided by 0.01. Okay, so natural log of 2 is something like 0.693 divided by 0.01. So it's going to take around 69 years for your money to double if you put your money in the bank. Okay, so gradually your money would increase, but it's not going to increase very quickly. In 69 years, you would have $2,000. Okay, that's pretty awful, right? I mean, that sort of goes to show you that you don't want to. If you want to, increase your money quickly, this is not the way to go. Right? Don't put your money in the bank. But think about in the old days when the stock market was giving 10% back, roughly 10% back every year. This happened until like up until the year 2000 or so. Right, from 1900 to 2000, on average, the stock market gave about a 10% return. Okay, so in that case, your rate is not 0.01, it's 0.1, right? Your rate is 0.1, which is great, because then what's going to happen? How long would it take for your money to double? 7 years, right? Or 6.9 years, or 7 years. So every 7 years, you put your money in the bank, your $1,000. 7 years, it becomes $2,000. By another 7 years, it becomes $4,000, et cetera, et cetera, et cetera. Okay, so that was good. I mean, even now, it's on average, it's like 6 or 7%, right? So 0.7. So about 10 years. There's about a 10-year doubling time. Okay, which is still pretty good, right? So when I was young, and I don't advise that you live like this, but this is how I lived when I was in my 20s. I think, okay, I'm in my 20s. There's about 40-some years left till I retire. Well, 40-some years, that's six doublings, right? 2 to the 6 is 64. So every time I looked at money, I think, do I want this money right now, or do I want 64 times it when I retire? Like, am I going to spend this $10 now, or do I want $640 when I retire? And I'm like, okay, I think I'm not going to spend this $10 now. Okay, right? For you guys, it's a little bit. So this resulted in me in not spending much money when I was in my 20s. I didn't have much money anyway, so that was also a problem. But then when I got married in my late 30s, my dad said, stop saving money. Stop saving money the way you've been saving, because that's not, it's okay for you when you're by yourself, but not when you're with other people. Right? Like, don't just save everything that you have. Anyway, but for you, the calculation is a little bit different, right? But not that much different. So 10-year doubling time, right? In your 20s, there's 4 or 5 doublings, right? So 2 to the 4th is 16, right? 2 to the 4th is 16. So 2 to the 5th is 32, right? So again, it's actually not that much different from what I was thinking, right? Every time you have some money, you think, well, do I want to spend this now, or do I want 2 to the 4 or 2 to the 5 times it when I retire? So anyway, okay. Same thing about borrowing money. Same thing about borrowing money, right? Because the interest rate for, if you borrow money, then I think the interest rate is probably around 5%, 4 or 5%, right? So the doubling time is about 12 years, right? If it's 5%, it's about 12 years, right? So you think, okay, if I borrow this amount if I borrow $1,000 now, then in 12 years that'll double. In 12 years it'll double again. Okay, so anyway, just something to keep in mind. People, it's good for you to. Something that a lot of people don't get about the world is exponential growth. Okay, right. That's how you grow your money. That's how you lose your money. Okay, right. I think this is a pretty. Even if you forget everything you've learned in calculus, remember this: exponential growth is your friend and your great enemy. Your great friend and your great enemy. Okay, so this is what's called doubling time. Notice about doubling time that doubling time doesn't depend on the initial amount. Right? Doubling time doesn't depend on the initial amount, right? Because your money, P of t being P naught e to the RT, well, you're asking when is 2P naught equal P naught e to the RT, right? You're solving this equation for t. But the P naughts get canceled out, right? The P naughts vanish from the equation, right? You're just asking when is 2 equal e to the RT, right? And that turns out to be natural log of 2 over r, right? So this is the doubling time. Right? This is the doubling time. Right? It's natural log of 2.693 something over the rate. Okay, so that's the doubling time. Okay. Okay. There's something similar for decay, which is the half-life, the halving time, basically. How long it takes to become half of what you started off with. Right? If you have radioactive material, then it decays, it decreases, right? And you're wondering how long it takes to become half, right? This sort of thing. So I don't want to spend too much time on it. So I'll just talk about the doubling time. I'm sorry. Let me just give one example of what's called the half-life. So, okay, so half-life. So, radioactive material decays like some constant e to the negative kT. Where I'm going to take k as positive and just write negative k to make it clear. To make it clear that there's some negative constant here. So given how long, given the half-life, the half-life, which is how long it takes to for the material to be reduced by half, one can calculate K. Okay, so this is sort of the opposite kind of problem. For those of you who haven't seen this yet, this is sort of the opposite kind of problem. In the first problem, in the doubling time, typically you're given a rate, and you want to figure out how long it takes to double. Okay. In the half-life problem, you're given a time, like how long it takes to become half, and you want to calculate the rate. Okay. So it's just a sort of opposite problem, but it's not all that different. It's the same sort of process. So, for example, the half-life of polonium is 139 days. So you've got this radioactive material, polonium. Every 130, you start off with a certain amount. Every 139 days, it becomes half of what it was, right? 139 days pass, you've got half of what you had. Another 139 days pass, you've got half of what you have. Okay. So if you wanted to describe the decay, so that is, you wanted to figure out what K is, right? Then, well, try it. Try and do it. If you haven't seen this sort of thing before, give it a try and see if you can figure out what K is. Okay, turn to somebody nearby and talk with them, please. Okay, so let me just explain this. You say, okay, I know, so the amount of your material follows this exponential decay model, right? So you know that right, it's just an experimental fact that the material decays like this. Okay. And you know that when the time is 139, that you end up with a half of what you started off with, right? You know that in 139 days, you're going to end up with a half of what you started off with, right? Okay. So just like before, we solve for well, now we solve not for t, but for k, but it's the same sort of thing. So you say, okay, natural log of 1/2 equals negative k times 139, right? Negative k times 139. Natural log of 1/2 is the same thing as negative natural log 2. Right, negative natural log 2. So what's k? K is just going to be natural log of 2 over 139. Okay, so this is kind of cool because now you know what k is, right? So you know how your material decays through all time. Right? You can figure out what happens through, you can figure out in how much material you're going to have in 140 days, 190 days, whatever you want. You know what's going to happen till the rest of time. Okay. Well, these are the sort of typical examples of exponential growth and decay. Okay. So we did exponential growth model. We also did the predator-prey model, right, where you've got the prey that are growing, but they're being preyed on at a constant rate. I want to do one last example of a differential equation, and this is called the logistic growth model. So this is just the beginning of a whole lot of different techniques that are used to solve differential equations. There's a course in differential equations. If you like this sort of stuff, you can learn a whole course worth of material on it. If you're a biologist or economist or something. Okay, so the logistic growth model starts like this. You say that you're modeling something, and the rate of change equals some constant times y times some m minus y. Okay. And so this is sort of a modification of the exponential growth model. Right? Without this term, it looks like the exponential growth model, right? Okay. So what is this? Why do people throw in this term? Well, as with the exponential growth model, as time goes on, the population goes to infinity, right? That's not realistic, right? Your population actually can't go to infinity, right? If you've got some sort of finite resources, right? That doesn't make any sense. That your population becomes infinite, right? So you see what happens with this term as you get closer to some maximal number. As y gets, so thinking like this, there's some number m, and as y gets closer to m. As y gets closer to m, well, your rate of change gets multiplied by a smaller and smaller number, right? So if you get really close to m, you're multiplying by a tiny number, and your rate of increase is going to shrink, right? If you actually hit m, then your rate of change will become 0, Okay, so this is saying that there's some sort of maximal carrying capacity for your system, right? That there's some limit on how big your population can grow, right? And so you throw in this term to say that that's what we, that's realistic for our system. Okay. Okay. So this m is some fixed constant that you think of as the maximal carrying capacity. Okay. Okay. So say, okay, well now we've got this logistic equation, right? Logistic equation, right? And let's solve it using separation of variables. So use separation of variables. Maybe I should write it as dy dt to make it look more like separation of variables. Okay. So I'm going to divide both sides by y m minus y. Going to multiply both sides by dt, right? And I'm going to anti-differentiate, right? Okay. So move everything involving the y's to the left-hand side, right? Move the t's to the other sides, do separation of variables, and then you take the antiderivatives. Okay. Well, on the right-hand side, you get kt plus c, right? Of course. On the left-hand side, how do you integrate something like this? Partial fraction decomposition. Right? So partial fraction decomposition turns out to be the way to do it. Turns out that you get 1 over m times 1 over y plus 1 over m minus y when you do your partial fraction decomposition. Okay. So you do your partial fraction decomposition, a over y plus b over m minus y, and both a and b turn out to be 1 over m. Okay. You can do it as an exercise if you want, but you should be well beyond that. Okay, right? So when you integrate the left-hand side, you get natural log of y in absolute values minus the natural log of absolute value of m minus y equals kt plus c. Okay. Consideration of the slope curves of the slope fields will tell you that if you're positive, you're always going to be positive, right? And you're never going to reach m, right? As you get closer and closer to m, the slope flattens out, right? So basically tells you that your solutions look something like this. Okay, so y is always going to be positive, and m minus y is also always going to be positive. You're never going to go above m. So we can get rid of the absolute values. So we get that natural log of y over m minus y equals m kt plus c. And so y over m minus y equals some constant e to the mkt. Where that c prime is really e to the capital M times the whole constant. Elizabeth? Yeah?
Oh, now I got it.
Yeah, okay. I just exponentiated both sides. Right, just exponentiated both sides. Okay, everybody all right? Like we made the logistic equation, and then we're solving it, and we get this, right? We get this. Everybody, any questions? Yes, Anna.
I don't really understand why you would want to solve it. Like
Well, it's sort of the same thing as before, right? You've got your exponential, you had this thing that you're modeling the growth of something, right? And you actually wanted to get a solution that told you exactly how things would happen. Same thing here, we've got some population, right? And you say, this describes it. I'd like to know exactly what my y looks like. We haven't finished solving for y yet. Okay, we still need to solve for y. Okay, so wait a minute, and you'll see that we'll get something very precise and likable. Tanima.
I think we might have gone over this last time. Why do you only add c to one side? But why do you take the integral of both sides and just add c to the...
I didn't mention it last time, but c is an arbitrary constant, right? So it's just some arbitrary constant that you don't know what it is, right? It's basically any constant, right? So if I add different ones to both sides, I could just combine them and say, well, I've got some arbitrary constant. Right? This constant is anything. This constant is also anything. Why not just call them c? Yeah, so that's what we do. Mr. Allen, did you have a question?
Yeah, I was wondering if that can be used also to find out the temperature or something if it cools off. I was looking at the very first statement you made there.
That's a different equation. So there is a so-called Newton's laws of cooling and heating, but that's not this.
Okay.
Yeah, that's not this. Yeah. Okay. So far we're up to this point. Okay. So now, if the initial population is denoted by y naught, we see that this c prime is going to be y naught over n minus y naught. Right? Because at time 0, this becomes 1. Right? At time 0, e to the 0 is 1, and we would get c prime equals the initial population over n minus the initial population. So then, so we have y over n minus y equals c prime times e to the mkt. Right? We just specified what c prime was. Okay, and then we need to solve for y, right? How do you solve for y? How do you solve for y? This is just algebra, right? Look, I've got y over n minus y equals something, right? Y over n minus y equals something. How do you solve for y? It's just junior high school again, right? You say, okay, I've got this thing, m minus y, right? So this is this times m minus this times y, right? You bring the y's over, so you get 1 plus this thing, oops, this thing, y equals this thing times m, right? And then divide both sides by 1 plus that thing. Okay. So that's just junior high school algebra. Okay. So you solve for y. You solve for y, and you get that y equals y naught m e to the negative kmt. So this turns out to be the solution of the logistic equation. Just like when we started with that, simple differential equation. When we started with that simple differential equation, we ended up with the exponential function. Now we start off with the logistic equation, and we end up with this function. Okay, and so this thing tells you how your function's going to behave, how your population's going to behave, based on those assumptions. Okay. What happens as t goes to infinity? What happens as t goes to infinity? What happens as t goes to infinity? Well, you've got this e to the negative kmt. Well, what will happen to that as t goes to infinity? People are murmuring, but nobody is talking. You got e to the negative, yeah, they are.
Tends towards 0.
Goes to 0, right? You've got e to the negative, basically this is e to the negative t, right? As t goes to infinity, that's going to go to 0, right? I mean, you've got some constants, but it's basically e to the negative t. Right, so this whole term is going to vanish as time goes to infinity, and then the y naughts will cancel off, and you go to m. Okay, so as time goes to infinity, your population is basically going to reach and sort of stay at its carrying capacity, right, which is maybe what's going to happen to humanity. Hopefully, if we haven't exceeded it. Okay. On that gloomy note, that's the end of class.